Alright, now we will work on the Lab 4 simulations, which is for the simple and Wilson current sources. So in LT-Spice, I've already put together the schematic for the simple source. If you did the hand calculations correctly, you should have gotten RF equal to around 1.8 kilo ohms once you round to the nearest standard value that we have in the lab. VDD and VSS are 5 volts, so having them in this orientation will make VDD plus 5 volts and VSS minus 5 volts. If you're not sure how to place the transistors, you go to Component and find NMOS 4, which is right here, and just place 2 of those. For the parameters, you just have to set the width and the length correctly. So if I go to the ones that I've placed, I've set the length equal to 10U, and the width to 1000U. The model parameters can get added with this .op option at the top, and click Spice Directive, and you can just type in what I have at the bottom here. .model, NMOS, and then followed by all the input parameters. We don't need the PMOS model since this is just an NMOS circuit. So for the output, you have a couple options to verify how this will work. One is you can sweep the output load resistance, which is what the lab specifies, but an easier way for you to generate your plots and get all the information you need is to just put a voltage source in parallel with the M2 transistor between the drain and the source. And if we sweep this voltage source, we can figure out at what point the output transistor goes into triode, and we can also figure out the output resistance as well by monitoring the current. So for my simulation setup, I'm doing a DC simulation, DC sweep, sweeping this voltage source here. And it's a linear sweep, 0 to 10 volts, and 10 millivolt increments. So if you run this sim, and it doesn't like a couple of the model parameters that I used, so you can just ignore that. But you can see the x-axis here is voltage for VDS, and we want to monitor the drain current at the output. And this should look pretty familiar from your class notes. If I turn on the cursors here, we can see right around this point here is when the device is going into triode. There's this large linear portion where the device is in saturation, and we can figure out the output impedance from that part. But if we go back to around 1.8 volts or so, that's the minimum voltage VDS for the transistor. So if we put a marker here, draw cursor position, it's 1.78 volts. I kind of ballparked it. That should be close to what the Prelab calculation gave. And the other part is to figure out the output resistance. So we can pick a couple data points when the device is in saturation and add a couple points like that. With this information, we can figure out the slope, which is directly related to the output resistance. So as the voltage changed about 3 volts or so, the output current didn't change a whole lot. It looks like 200 microamps. And so you can use those 2 data points to figure out the slope, and the slope will give you the output resistance. In this Excel sheet for this, we need a picture of the schematic. So you can use snipping tool to get a snapshot of that along with a snapshot of this plot up top. Once you have those, you can put those in these two boxes. And I just measured VDS min for you. You should get something similar. You can calculate RL max just based on that VDS min value, and the same way you did for the Prelab calculations. So VDS min is about 1.8 volts. That means at minus 5 volt supply, the minimum VO can go in this schematic is about minus 3.2. If you put a resistor between VDD and that minus 3.2 voltage for 4 milliamps, you can calculate what that resistance would be, and that would be RL max. And output resistance you get from the slope of the output while in saturation. And we just need to replicate that same sim for the Wilson source. So I'm going to close out of this. You can save this off so you can submit it later. I don't need to save it because I've already done so. And I'm just going to open up my Wilson source sim. So if you did the Wilson calculations correctly, our ref is close to 1.2 kilo ohms if you have a plus or minus 5 volt supply. The model parameters are all the same. Just make sure W and L are 1010 for all the devices. And we're going to do the same sweep at the output and make the same measurements. But we expect the Wilson to be much flatter. The output current should not change significantly at all as we change this output voltage. And that's because it should have a higher output resistance based on the theory. So doing the same DC sweep here, VDS 0 to 10 volts and 10 millivolts increments. And again, it's upset about my modeling parameters. You can probably leave those off for your sims. And there we go. So I've already gotten a couple of data points here. They're about 1 volt apart, and the current changes by, let's see, 678 to 687. Looks like it changed by 10 microamps, which is about 10x better, I think, than the simple source, roughly. And it's kind of hard to tell where the cutoff is between triode and saturation, but it's probably, I don't know, somewhere around here is where it looks like it takes a dive. So about 4 volts VDS, which corresponds to a V out of minus 1 volt. Because if this is minus 5 volts, you go up 4, V out is minus 1. So that looks to be about the minimum voltage you can have here. And again, you can figure out what kind of resistance that would be to VDD. VDD is 5, VO is minus 1, so delta V is 6 volts, equal to IR, where the current is about 4 milliamps. You can calculate what that max load resistance is. So again, get a picture of the schematic, picture of this waveform up top. VDS min was about 4 volts. RL max, I just told you how to calculate it, and R out you can get from the slope of the output here using a couple of data points. And that's it. When you're done, just make sure you save off all your LT-Spice files, you have all of your pictures, and you submit all of this to my courses.